To be without video today, at least without video of me, but I'm not that important, so let's just look at the slides and we'll go from there. So today we're going to talk about Gaussian graphical models. So, okay, you've seen Gaussians before. Their distribution over a variable in Rn. And if we have a whole bunch of continuous variables in our set of observations, it's going to turn out that Gaussians are a really nice tool for modeling the dependencies among all of these variables. So the first thing I want to point out is that Gaussians are an exponential family. So we mentioned this before, but I wanted to specifically take a look at the density again. So here is a Gaussian density. And what I've done is I've assumed that the mean is 0, so there's no mu in here. And I'm using the precision, which is the inverse of the covariance. And since matrix inverse is a 1-1 function for positive definite matrices, difference, we can use either the precision or the covariance as our parameter. And with those assumptions, this is what our density is, right? We have a normalizing constant that depends on the parameter omega, and then we have e to the minus quadratic, where the quadratic is minus a half x transpose omega x. And if we look at this in the density, the only interaction between the random variable and the parameter is in this expression right here, x transpose omega x. And that expression is linear in the parameter, which tells us that the Gaussians are an exponential family of densities, right? Because an exponential family is something that we can write in the following form. We want to be able to write it as e to the t of x dot theta minus g of theta, right? There's also optionally a base density, which I'll call p0 of x, although that's going to turn out to be uniform here. So if we can put it in this form, then it's an exponential family of densities. And so if we make these definitions here, right, so if we write in particular t of x equal to minus a half x transpose, right, then, and if we write theta, the parameter, just to be the precision matrix omega, then t of x dot theta is I'll write dot here and I'll put it in quotes, right? Because these are actually both matrices, and so I'm using the matrix inner product, which is all right. So apparently, in addition to the video being not present, I was having audio difficulties. I'll just try and make sure to write everything so that what I say is clear. Apparently they're starting to resolve now, so I'll just make sure to write everything and let me know if something isn't clear. All right, so t of x dot theta, that's this part right here, that's equal to minus 1/2 x transpose omega x, right? And so that is this part of the density. And then this part here, we're just going to capture as e to the minus g of theta. By the way, the TAs tell me that if you refresh your page, sometimes it helps problems with sounds. And I'm being told that the audio is still a little problematic, but is starting to get better. So hopefully it continues to get better. All right, so taking this value of the statistic t and the normalizing log normalizer g, we can write our probability as e to the minus t dot parameters minus g of parameters. And so that represents the Gaussians as an exponential family. Now, that means that the Gaussians are the answer to a maximum entropy problem, right? Every exponential family is the answer to a maximum entropy problem, namely maximizing entropy while constraining your observed average statistics to be equal to the statistics that you get from your parameter. And so that's this constraint here, the expected value of t of x, maybe even in more detail, the expected value of t of x given our parameters, which is omega, should be equal to t bar, which is equal to the average value of our statistic here in the data, which is to say minus 1/2 sum over examples xt transpose, right? And this here, right, is actually minus 1/2 times the covariance of x. So there's a missing minus 1/2 there. That's basically saying that the Gaussian distribution is the distribution that maximizes entropy subject to having a specified covariance matrix, right? Which is kind of a nice way of thinking about it, right? It's just given the covariance matrix that you observe, make the fewest possible additional assumptions, and that gives you a Gaussian distribution. Now, I'm not going to derive it, but the same thing also holds for the mean. The Gaussian is going to maximize, for a non-zero mean, the Gaussian is going to maximize entropy subject to having a specified mean and covariance. All right, so that's great. We talked about max-end distributions before, and there was in particular one useful idea for max-end distributions, which is this idea of sparsely connected features. So each one of our features, right, Tij is the expected minus 1/2 times the expected value of xi times xj. And so Tij depends only on the coordinates xi and xj. And that's an example of being a sparsely connected feature. And with sparsely connected features, we use this idea called a factor graph to tell us which features directly, which coordinates of x directly connected to each other via the features. And so we can draw a factor graph for a Gaussian distribution, and it's going to look like this. So here is a factor graph for 1, 2, 3, 4, 5, 6 different components. So x is in R6, and every pair of components of x is connected because there's one feature Tij that connects each pair xi and xj, right? Now, so this factor graph is simple in a few ways. One of them is that all of its edges are actually edges and not hyperedges, and so I've drawn them just as edges instead of using the convention that we did a few lecture notes ago of having a little box that let you connect an edge to multiple variables. So these are just plain edges, each connected to 2 random variables. The other is we've also skipped all of the self loops, right? They're present. There's a feature, the diagonal elements of T connect xi to itself, but we're going to skip those because that's conventional when you're drawing a graphical model. All right, now this is maybe not a very interesting factor graph because it's just fully connected, but we can be a little bit more interesting if we do the following. We can constrain some of our precision matrix entries to be 0, right? And what that means then is that we're going to just ignore some of our features Tij. Right? If we constrain the corresponding parameter to be 0, it doesn't matter what the value of the corresponding feature is. And so when we do that, we can just remove those features from our Maxent distribution, and that's the same as removing those edges from our graphical model, and we might get something that looks like this, right? And this is now going to be a pretty interesting graphical model. And it's called here a Gaussian graphical model. If you want to emphasize that it's missing some edges, you say a sparse Gaussian graphical model. And it's actually a pretty powerful tool for modeling a multivariate continuous distribution. And if you remember, because this is a Gaussian distribution, all of its single variable marginals are Gaussian. And if that doesn't agree with your data, we talked several lectures back about this idea of a copula that lets you fit non-Gaussian marginals. We're going to ignore that for today, but just keep in the back of your head that if your marginals aren't Gaussian, you can actually fix that problem by using a copula. All right, so going back to just plain Gaussians, we have a sparse Gaussian graphical model. And the reason it's powerful is sort of twofold. One is that we can control, by controlling this graph structure, which variables are dependent or independent or conditionally independent of one another. And that's true for all graphical models. But what's not true for most graphical models is that there are actually efficient algorithms for doing things like marginalizing and conditioning and doing, other sorts of inference operations in a Gaussian graphical model. And so the rest of today's lecture, we're going to be talking about what are those algorithms, because they're actually pretty simple. And so they're useful to know. And so we have a lot of the power, Gaussian graphical models give us a lot of the power of general graphical models to flexibly specify which variables are statistically dependent or independent of one another. But unlike general graphical models, we don't pay nearly as high a price. We're able to do lots of useful operations with Gaussian graphical models efficiently. Now I wanted to point out that, again, we're emitting self-loops in our graphical model. And the self-loops correspond to that is correct. Somebody pointed out that I forgot to draw the edges directly across this graph. That's actually just a typo. I'll fix it after class. The graph that I want is truly the fully connected graph the way I said, right? So that's going to have all of those edges as well as not sure. There. All right. So this is the graph that I actually mean, and I'll update the notes after class. Thanks for pointing that out. Anyway, the point is that instead of the fully connected graph, we would like to use a non-fully connected graph, like this one. And so we've omitted self-edges, which correspond to the diagonal elements of the precision matrix. And we're going to assume that all diagonal elements are allowed to be non-zero, because if you try and force one of them to be zero, then your precision stops being invertible, and we'd always like to have an invertible precision. It makes our lives much easier. So we're going to assume that all of these self-edges are present, even though we don't draw them. All right. So what are the operations that we want to be able to do? We'd like to be able to given a Gaussian graphical model, we'd like to be able to marginalize out a variable or condition on a variable. We'd like to be able to fit the parameters of one of these graphical models, and we'd like to be able to reason about conditional independences. And so we'll go through each one of these operations in turn and describe the algorithms that you can use to do them. So the first one is conditioning. And the conditioning is straightforward. So we're going to start from our prior density, which is e to the minus quadratic. It has the form like this: e to the minus a quadratic in our variables divided by a normalizing constant. And then we're going to just fill in the values of the variables that we observed. So if we observe that the fourth component of x is 7, we just fill in 7 in place of x sub 4. And then that's going to give us the unnormalized posterior density, and we get the posterior density by just renormalizing. Now, because the prior is of the form e to the minus quadratic in x, the posterior is also going to be of that form, because if you fill in some of the variables in the quadratic, all that does is it takes some of the terms in the quadratic and it reduces their degree. It takes second degree terms and turns them into first degree or constant terms, and it takes linear terms and turns them potentially into constant. Right? And so let's do that just in a little bit more detail. So here's the quadratic part of the prior density, x transpose omega x. This corresponds to a Gaussian with mean 0 and precision omega. And let's arrange x so that the component that we observe is the last component of x. So that means that we can partition our variables like this. Our vector x is u, which is all of the variables we didn't observe, and then v, which is the value that we did observe. And omega has a, which is the precision block that corresponds to u, c is the precision block that corresponds to v, and then b and b transpose are the cross precision blocks between u and v. Right? So a is r n by n, b and u are n vectors, and c and v are scalars. And our goal is now to calculate the posterior density over u. So we can split up the quadratic part of the prior, right, like this, right? So if we take u v transpose a b b transpose c times u v, right? Like that. That's equal to u transpose a u plus 2 u transpose b v plus v squared c, right? Which is what I wrote here. Right? And the way you can do that, right, is you just take every possible way of taking an element of this and an element of this and the corresponding block of the precision matrix. Now, this last term right here, that doesn't depend on u. Remember, we're trying to get the posterior over u, and so we can just drop this. This will get absorbed into the normalizing constant. And then for this here, what we're going to do is we're going to complete the square, right? So we can rewrite this term as 2 u transpose a inverse a b v, right? Just multiply by a inverse a, which is the identity. And then we can add and subtract. So we're going to wind up getting, right, basically we're going to wind up getting, as part of the quadratic, well, here, we can see it in this term, right? We're going to get a in the middle of the quadratic. So actually, I wanted to multiply by a times a inverse like that. So a is going to be in the middle of the quadratic, and we're going to get u and a inverse bv as our two sides of the quadratic, right? And so what we have to do then is add u transpose a, we have to add the last term, right, which is v b transpose a inverse a inverse b v, and minus the same thing. And if we do that, we can factor out and we get u plus A inverse B V transpose A U plus A inverse B V. So all I did here was I completed the square, right? And I wrote the same thing here, and we get there's going to be a constant as well. Right, and so I wrote that here. And so what we've done by completing the square here is that we've gotten a quadratic in U, which is our variable, and we can pattern match this against a Gaussian density, right? So this is the quadratic part of a Gaussian density with precision A, because there's an A in the middle, and mean minus A inverse BV, right? So what have we just shown? We've shown that if we condition on the last component of x being v, the posterior over u becomes a Gaussian with precision A and mean minus A inverse BV, right? And so conditioning on an element of a zero mean Gaussian means basically that we delete the corresponding row and column of the precision matrix, right? We drop B and C because they correspond to the element that we're fixing. And then we set the mean for all of the other elements to the thing we just calculated. Right? So this is an efficient algorithm for conditioning in a Gaussian graphical model. The time required is basically the time to solve this system of linear equations, right? Which is no more than cubic in the length of the vector b. And so in order to keep the math simple, I used a zero mean Gaussian, but we can handle a non-zero mean Gaussian just by subtracting the mean, conditioning, and then adding the mean back in. And so the update becomes becomes as follows. The precision matrix is the same, right? There's no change to the precision matrix when you add and subtract the mean. And so the precision matrix will still be A. And the update to the mean, so we can partition the mean into the mean of U and the mean for V. And all we do is we update the mean for U by adding that same increment that we calculated for the mean based on the observed value V. And here, because we're adding and subtracting the mean, we wind up getting the difference between V and its mean in place of just plain V, where it was before. All right. So this lets us condition on elements of our vector. And if we want to condition on several elements, we can do them one at a time. Or we can use, there's a block version of this update formula for the mean, right? So the update for the precision is still that you drop all of the corresponding rows and columns of the precision. And there's a block version of this update for the mean, which is essentially as you would expect. But I don't remember it off the top of my head, and so I won't try and write it on the slide. All right, so that's conditioning. The next thing that we want to do is to be able to marginalize out a random variable. And in some ways, that's actually even simpler than conditioning, even though if you try and write down the formula, it's actually a little bit more complicated. So to figure out what happens when we marginalize, all we need to know is that every marginal distribution of a Gaussian is, again, Gaussian. And so all we need to do to figure out the marginal distribution is to figure out its mean and covariance. So to figure out the mean, well, the mean of a variable I is not affected if we drop any other variable, right? Like if we decide that we just want to forget about variable xk, that doesn't affect the mean of xi. And the same thing for covariance. If we have the covariance between two variables xi and xj, and we drop a third variable xk, that doesn't affect the covariance, right? Because the covariance is just defined as the expected value of the product of xi and xj, and that expected value does not contain xk at all. And so it's actually really simple to compute the mean and variance of the marginal distribution because they're the same as the mean and variance of the original distribution. Except that we just drop the components corresponding to the variables that we're marginalizing out. So here's the algorithm, right? We start with our precision omega. We compute the covariance, which is just the inverse of the precision. We drop the row and column of sigma corresponding to the variable we're dropping. And we drop the element of the mean vector corresponding to the element that we're dropping. And so I'll write sigma prime for the smaller covariance matrix and mu prime for the smaller mean vector. And mu prime is just our new mean vector, and our new precision is just the inverse of the updated covariance. So marginalizing and conditionalizing are dual to each other in some way. To marginalize, we're going to drop rows and columns of the covariance, and to condition, we drop rows and columns of the precision. Right? And so if we want to both marginalize and condition, we'll do the marginalizing in covariance form. And then when we switch, we can invert to get to the precision and do our conditioning, right? And if we alternate, we can go back and forth. And I just got a question of whether that's equivalent to recursive least squares. Yes, it's also equivalent to a Kalman filter, if you've seen that. You can write, if you think about it, a Kalman filter is just a very large Gaussian graphical model that ties together the state at times 1 through t and the observations at times 1 through t. And so you can derive both a Kalman filter and actually a ton of other interesting linear model operations as special cases of the Gaussian graphical model. It's one of the reasons the Gaussian graphical models are so powerful. All right. So I described marginalization as inverting, deleting some rows, columns, and inverting again. But that's not actually as computationally efficient as it can be. It's not bad. It's still poly time. But you can actually do a whole lot better. And so I wanted to mention that. Basically, the algorithm that you use is called the Schur complement formula. And what that is suppose that we have our precision matrix omega partitioned like this. And we're going to try to marginalize out the last row and column, right? So what we want to do is invert, delete the last row and column, and invert again. But the Schur complement formula says that we can do that without doing two matrix inverses. Basically, the resulting omega prime is just this block minus B C inverse B transpose. Right? And this expression here is called the Schur complement of C in this matrix omega, named after the guy who discovered it. And there's also, so doing marginalization this way, right, we only have to compute 1 over a scalar instead of inverting a matrix of size approximately n twice. And it turns out that there's also a block version if we want to do a whole bunch at once. So if we partition omega like this, A, B, B transpose, and C, where these are all matrices, n by n, k by k, and the exact same formula applies. Omega prime is just A minus B C inverse B transpose, which is again called the Schur complement of the block C in this larger matrix omega. And we still need to compute a matrix inverse here, but as long as C is a small matrix, then we're going to save a lot of computation compared to doing it naively. Somebody wanted to know whether polytime is a good or a bad thing. So I'm thinking of polytime as being a good thing in this case, because ordinarily with graphical models it would take exponential time to do any of these operations like marginalizing or conditioning. And so rather than exponential time, having you be able to do it in poly time is a big benefit. Let's see. There's a question also about why we would want to condition or marginalize. So the situation is this: we've got some data, a whole bunch of x's. We fit a Gaussian graphical model to that data, which I haven't described how to do yet, but we'll get to it in a couple of slides. Once we fit that Gaussian graphical model, we now want to make predictions. And the sort of predictions we could make are, suppose that somebody reveals, let's say, the first 3 elements of our random variable x, so reveals x1 through x3. What do we then know about the remaining elements of our random variable? Let's say it's 6 elements, so we reveal 1 through 3, and we want to predict 4 through 6. So that's conditioning. We condition on x1 through 3. And marginalizing helps in sort of more complicated prediction scenarios. Suppose that we know that we're not going to observe x4, but we are going to observe, let's say, x1 through 3, and we want to predict x5 and x6. Then what we want to do is marginalize out x4, condition on x1 through x3, and then we'll get a Gaussian distribution over x5 and x6 that we can use to make predictions. Right? So we want to be able to do all of these operations, fitting the graphical model and marginalizing and conditioning. We want to be able to do them efficiently in order to be able to make predictions. We just talked about how to do marginalizing and conditioning efficiently. Let's start talking now about how to fit a graphical model to a bunch of parameters. Let's see. So we're going to start, for fitting, we're going to start with an IID sample that's drawn from a distribution that's represented by a Gaussian graphical model. Right? So we have, let's say, n sample vectors. We're getting apparently still bad video freezing. I don't know what's changed. There's been for the past couple of lectures, we've had bad video problems. Let's just check and see if I can just briefly diagnose what's going on. Yeah, no, it claims that I'm... I don't know, maybe the network is ready for Thanksgiving break. That's the only explanation that I can think of. I'm hearing that people don't miss content, that it just pauses for a couple of seconds and comes back. I'm going to see, I guess I'll try in between. Yeah, I'm getting a recommendation. I'm going to stop the stream and start it again. And that seemed to help last time. So let's do that. I'll stop the stream and we'll restart it. And hopefully that will fix things. All right, so I should be back. So let me know if the stream still has problems. I've also been told that if you pause briefly and then continue so that you have a little bit of extra buffer, that seems to be helping some people. All right. Let's see. All right, so where were we? We were talking about now maximum likelihood in Gaussian graphical models. So we start with an IID sample, and what we assume that it's drawn from a Gaussian graphical model with mean mu and precision omega. but mu and omega are hidden. They're not given to us. All that's given to us is the structure, which is to say which of the off-diagonal elements of omega are constrained to be 0. And so let's say that we have a set Z of elements of omega, I comma j, and we're going to constrain omega ij to be 0 for all ij in Z. And we'd like to estimate mu and omega by maximum likelihood. So it's fairly straightforward to derive that the maximum likelihood estimate for the mean is just the empirical mean, the 1 over n times the sum of all of our data, and that doesn't depend on the structure of omega. And so what we're going to do is we're going to skip talking about that. We're just going to assume that the mean is 0, and we'll look at estimating the precision omega. And what you would do in practice is just you would estimate the mean first, and then subtract it off, and then estimate the precision from that 0 mean data. All right, so our log likelihood, right, is the log of the probability of all of our x's given omega, which is to say, right, if we go back and take a look at the Gaussian density here, right, basically the part that there's square root of the determinant of 2 pi omega, and there's e to the minus half x transpose omega x. So if we go back down here, right, we get log of the square root of the determinant of 2 pi omega minus a half sum over all of our, sorry, there should be an n here because there's n copies of this. It comes back down here. So there's a typo in that term. Minus a half times the sum over the x's of x transpose omega x, right? And so we can pull out the factor 2 pi if this is a d-dimensional Gaussian. We get nd log square root of 2 pi. The square root becomes a half when we take the log, so we get a constant term. Then we get n times the log determinant of the precision minus n over 2 times that, minus n over 2 times the dot product between omega and the empirical covariance, right? I've just collected terms here, and I've used trace rotation to bring all of the covariance elements together. So, right, all of these linear algebra operations, by the way, should be familiar if you went over the notes from Mini 1. So we'll assume that new people in Mini 2 who haven't seen this before can go back and take a look at the notes from Mini 1 about things like trace rotation. All right, so basically we've got the log determinant of omega, and we've got the dot product between omega and the empirical covariance matrix. So that means that if we ignore the structure, we can find the unconstrained MLE by taking the derivative and setting to 0. So if we take the derivative of L, the constant goes away. The derivative of the log determinant, you can look that up, or you can remember it from the first mini, is the trace of omega inverse transpose times d omega. And then the differential of this one, this is linear, and so the differential just passes through, and we get trace of c transpose d omega. So if we set d omega to 0, that means that its coefficient has to be 0. And its coefficient is omega inverse minus c, right? So that just says that omega inverse is c, which is maybe not surprising. It says that the best estimate unconstrained for the precision is just the inverse of the empirical covariance matrix. All right, so that's without constraints. If we want to do it with constraints, it becomes a little bit more interesting. And we actually are going to wind up needing a technique that we haven't covered yet. We're going to cover it in a few lectures. It's called Lagrange multipliers. And so I'm going to skip over for now what you do with the Lagrange multipliers and just skip to the answer, which is that instead of setting omega to be the inverse of the empirical covariance, we set it to be the inverse of the empirical covariance plus a correction term, lambda. And lambda is going to be 0 whenever, for all of the elements of omega that are allowed to be non-zero. And lambda is going to be non-zero wherever omega is constrained to be 0. So the zero pattern of lambda is the complement of the zero pattern of omega. And so all we have to do is find lambda in order to be able to do constrained maximum likelihood. And here's an algorithm for finding lambda. We just repeatedly update lambda by a learning rate eta times a step matrix delta, which is defined like this. We just take our current lambda and we invert it. And basically, we take a non-zero step wherever our current precision is non-zero and is supposed to be 0. Right? So it kind of makes sense. Right? This is our current precision, C plus lambda inverse. And wherever it's allowed to be non-zero, we do nothing. Wherever it's supposed to be 0 and is not, we take a step. All right. So this algorithm, you can implement it in half a dozen lines of MATLAB. It's not the most efficient algorithm for doing this sort of estimation, but it's really, it makes up in simplicity what it lacks in efficiency. And it's just fine whenever you're dealing with, let's say 100 or fewer variables in your graphical model. If you want to handle larger graphical models, then, well, I guess start looking at more advanced machine learning and optimization courses, because there's a lot of really interesting stuff for figuring out how to optimize models like these. All right, so this is how, if we know the structure, this is how to estimate the parameter omega. And if we don't know the structure, it's actually possible to estimate the structure as well. And it turns out that there are, just like for estimating the parameters, there's a huge variety of algorithms that people have proposed for estimating the structure. I'm only going to describe one of them. And we picked this one not because it's the best, but because it's fairly simple and it uses only ideas that we've covered so far. And the idea is basically that there's a connection to linear regression, and we can optimize the jth row and column of omega by fitting a linear regression model to predict. We can optimize the structure of the jth row and column of omega by fitting a linear regression model, a sparse linear regression model, to predict xj from all of the other components of x. Right? So because we can do that, structural learning basically reduces to variable selection. We just choose the non-zero elements of the jth row and column of omega by running a linear regression to predict the jth element of x from all of the other elements of x, and using variable selection to decide what are the relevant predictors. And in particular, for example, we can use forward selection or forward stage-wise regression, which is an algorithm that we went over last week for doing variable selection, right? So the way that looks is separately for each element of x, we run a forward stage-wise regression, and we use a bootstrap error estimate to decide when to stop letting variables enter the regression. And then we use the non-zeros that we've learned to tell us the structure of omega. We let omega ij be non-zero, either if xi had a non-zero weight in predicting xj, or if xj had a non-zero weight in predicting xi. Right? And like I said, there's a ton of variance on this approach. We could use a different variable selection method like lasso. We could use a different method for combining the results. Or we could actually use an iterative method where we repeatedly estimate the structure for a given row and column of omega, given what we've learned so far about the structures of all of the other rows and columns. And there's an example of an algorithm like that that's described in one of the recommended textbooks, Elements of Statistical Learning, and I put the link to that in the syllabus. All right, so that's Gaussian graphical models. They're a really pretty useful tool, and they're efficient to work with. And what I wanted to do was just give you guys a few a few exercises on a very simple Gaussian graphical model, just to let you practice and see what these operations actually are like when you implement them in practice. So what I'm doing right now is posting to Piazza a Q&A link. Oh, looks like it didn't come out as a link. Let's see if I can fix that. All right, it's up now as a link, and I'll just bring it up here. So you're given 4 samples from a random variable, and what we're asking you to do is to estimate the covariance, estimate the precision from this data, either with no structure assumed or with some structure assumed, and then use the result to do a marginalization and a conditioning operation. So what we'll do is we'll just, I'll pause the lecture here, and please have a look at this and ask questions if you have any questions. Because there's already a homework assignment due today, we're going to make this due tomorrow at midnight, so that you can spend the time outside of class working on your homework 1 programming. But hopefully for the rest of class, you can take a look at this and ask questions if you have questions. Hi all, I just wanted to point out that I posted the pseudocode, posted MATLAB version of the pseudocode for gradient descent parameter estimation, right? So the algorithm that I described right here in section 9, I just posted MATLAB code to go with this pseudocode right here. And so if you want to use that, it should be quite easy to translate the MATLAB code into any other language you want, like Python, if that's your preference as well. Hi all, I'm getting some questions about how to calculate the precision matrix that we're asking for. So that's basically what we're covering here, right? So the precision is defined to be the inverse of the covariance matrix of your Gaussian. And here, this is the way sections 8 and 9 of the notes tell you how to estimate the precision matrix from data, right? And we do it based on the empirical covariance matrix C here, right? And there are two cases which we ask you about. Both of them we ask you about in the Q&A. One of them is unconstrained, where you don't constrain any of the elements to 0, which is omega inverse is just C, right? So the precision is the inverse of the covariance. And the other is constrained, which is this algorithm right here, right? So there's pseudocode in this section, and then I actually also just posted MATLAB code for this same algorithm to Piazza. So hopefully that resolves the confusion about how to calculate a precision. If not, please ask some more questions and I'll try and answer. All right, so we're getting still some questions about how to get started fitting a precision matrix. So let's go back to here, right? So in general, whenever we want to fit the parameters of a model, right? So we have we're trying to make a model that says that we have a vector x, and we want p of x given some parameters, which in this case is our precision matrix, is equal to, and we have an expression for that, right? It is the square root of the determinant of 2 pi omega e to the minus 1/2 x transpose omega x, right? So this is our model, right, for our random variable x. And when we fit it by maximum likelihood, that means that we have a sample here, right, a whole bunch of IID samples from x, and we want to figure out what is the value of this parameter that best explains the data that we saw, right? And so what we want to do is we want to find omega to maximize p of x given omega, right? And I should say, actually, maybe even better, p of all of our data, x1 up to x, x1 up to xn given omega. And so that's what we did here in section 8, right? We maximized this expression, right? So it's equivalent, by the way, to maximize the log of that expression, because log is a monotone function. So we maximized the log of that expression by differentiating and setting to 0, right? And so we did a bunch of algebra and derivatives, and we got this expression, right, that the inverse of the precision matrix equals C, where C is described this way, right? It is the empirical covariance matrix. Empirical just means derived from data. So what this means is the covariance of x, right? So we know that covariance of x is equal to the expected value of x transpose. That's just the definition of covariance. And so the empirical covariance is you replace the expectation by the mean over our data points, right? And so when I say fit a Gaussian with 0 mean to the data x1 through xn and report back the precision matrix, that means find the precision matrix by maximizing this probability, or this log probability. And that means to go through this math. You don't actually even have to go through the math. You just have to look at the end of the math, which is the equation that omega is equal to C inverse, right? So hopefully that clears up what I mean by fit the precision matrix. And section 8 here describes how to fit it with no constraints, and section 9 describes how to fit it when we're constraining some elements of the precision matrix to be 0. Right? And that's this pseudocode here, and then there's corresponding MATLAB code that I've posted to Piazza. So please continue to ask questions if there are, if that doesn't clarify things, and we'll, keep going on the exercise. All right, everybody, this is the end of class, so please continue to ask me questions. My office hours starts now, and after office hours you can ask questions on Piazza as well. All right, talk to you guys later. Have a great Thanksgiving.